Hey, thanks for joining our virtual presentation. I'll be walking you through our paper that has been accepted at ICCV 2025. This is a joint work with my amazing collaborators, Leonid and Rogerio from the MIT IBM Watson AI lab. Traditional machine learning methods assume that the training and test data are drawn IID from the same distribution. However, when the test distribution or your target distribution differs from the training distribution, or we call it source here, we face the problem of distributional shift. And such a shift poses significant challenges for machine learning systems deployed in the wild. For example, consider a pre-trained or source model with parameters theta of s. During deployment, while the visual world is huge or large, one can encounter images with noise or blurry images or visuals corrupted due to weather conditions or where images can be affected due to compression. So there's a growing body of work, especially for pure vision models, and they propose that learning during training alone is not enough and that performance can be improved during testing by test time adaptation during deployment. However, our world is inherently multimodal. Distributional shifts in deployment settings introduce cross-modal inconsistencies. Such shifts can be even more detrimental since they undermine the complementary nature of modalities, and it can actually cause models trained under clean, balanced conditions to fall unpredictably. In this work, we focus on vision language models, and in particular, CLIP. Ideally, our method can be extended to other vision language models as well. And CLIP has emerged as a foundational architecture for aligning visual and textual representations. While CLIP demonstrates remarkable, zero-shot generalization, it remains highly sensitive to corruptions and distributional shifts in either the vision or language modality. I'll be talking about this very soon. So we are all aware of the usage of CLIP as a foundational model because of its strong zero-shot capabilities, all thanks to the supervision from massive corpora of paired image language data. In this section, we study if CLIP's feature space can be transferred under image distributional shifts. We'll be focusing on two primary areas, zero-shot performance and the need for adaptation to address domain shifts effectively. Again, this brings back to what we're working on. So the first question that we want to answer is the feature space of CLIP transferable at test time under distributional shifts? And can it infer under new contrastive associations? So as a simple experiment, we consider covariate shift. That is, the label spaces between the source and target or test data are the same, but the input test data is shifted. In the figure, we show zero-shot evaluation of CLIP with a VITB16 backbone on ImageNet C that consists of 15 types of corruptions. Despite CLIP's robust multimodal feature space, you can see that accuracy drops significantly with an increase in corruption severity. And as can be seen, compared to zero-shot CLIP on ImageNet, which has an accuracy of about 67.7%, and that can be seen with the black bar, the mean accuracy on ImageNet C is as low as 24.5% at a severity level of 5. And we have additional results in the main paper, but overall, the reason for this performance is, or a plausible explanation for CLIP subpar performance is that the parameters of the image or visual encoder were not optimized for such corruptions during pre-training. In zero-shot classification, the visual features from a given domain may lack the robustness and richness necessary that's necessary to align well with their corresponding text features. And because of this sort of results in lower likelihoods. So the major takeaway is that testing data varies in many ways in the real world, yet our models are the same and they fail to generalize. In this analysis, we evaluate the impact of prompt engineering by providing, sort of relevant prompt templates to the text encoder at test time. Each prompt will add, it'll add more context to help CLIP extract more relevant text features. So the setting is same. We have covariate shift in images, and the question that we want to answer is, will different prompt templates help? Here, we report the mean classification accuracy across ResNet 101, VITB 16, VITB 32, and VIT large 14 backbones at an image corruption severity level of 5 for all the datasets. The datasets here are CIFAR 10C, CIFAR 100C, and ImageNet C, and we vary the prompt templates. So for each dataset, the x-axis is a source accuracy, and your y-axis is the mean accuracy across 15 tasks on each of the respective datasets. It is interesting to observe that irrespective of the backbones used, we do not see any drastic changes in the mean accuracy. And a key reason for this is that despite the use of relevant prompts at test time, the text and visual features remain largely independent and unaware of one another, which leads to poor associations of image text. To add on to this, it is impractical to perform prompt engineering or optimize prompt vectors at test time, especially during deployment, right? As choosing different prompt templates for generating text features is extremely tedious and it's pretty time consuming. Also in real-time deployment, which involves prompt tuning of small or shallow vectors, such prompts cannot quickly estimate the distribution of incoming test batches. Um, Now that we have seen that the zero-shot visual encoder of CLIP is very, very sensitive to image corruptions with a decline in performance when the severity increases, and the text encoder is pretty much invariant to the different prompt templates. So there's a need to adapt slash fine-tune CLIP at test time. In essence, both the encoders need to be adapted to the incoming domain of test batches to focus on achieving strong image text alignment and feature separability. This brings me to the overall framework of test time adaptation, where the source model, in our case CLIP, is adapted to an incoming test batch, where only one single forward pass is allowed, and we call this online learning. And this test batch is observed only once due to data privacy. We also have we do not have access to the pre-training dataset or the source data, which is again due to privacy. So the model, or let's say CLIP in this example, has to be adapted on the fly to unseen data at test time. While there have been prior works or very few works on using CLIP for online TTA, they come with certain limitations. For example, this work, test time prompt tuning, tunes the text prompts on the text encoder alone and generates multiple random augmented views for each test image. The text prompts, which are initialized to pre-trained values, are optimized by minimizing the marginal entropy of the confident model predictions. However, if you observe, such a method is expensive and slow due to performing multiple forward passes through the vision encoder of CLIP for each image. Also, it relies on handcrafted prompts for initialization, which pretty much makes it impractical at test time. Another recent approach, Vision Text Space Ensemble, uses an ensemble of different prompts as input to CLIP's text encoder while keeping both the encoders frozen, which is okay, which is fine. But since the vision encoder is frozen, it struggles to effectively adapt to images with severe noise because of a lack of alignment between the text and visual features. So as we can see, so TPT remains primarily a unimodal approach, and this limits the capacity of a multimodal model like CLIP to fully leverage its multimodal nature for adaptation. Specifically, it prevents the encoders from jointly adjusting their features, which results in suboptimal alignment between the visual and text modalities after adaptation. So to address these core issues, we propose a bimodal adaptation scheme for online test time adaptation of CLIP, where both the encoders are adapted to enhance image text alignment and also achieve a high separation of visual features. And to make this entire thing very parametric efficient, we adapt only the layer norm parameters of both the encoders. So our method is very general purpose and with no reliance on multiple prompt templates or their ensembles, unlike VTE. As a teaser, our method achieves SOTA results on the benchmark datasets, as you can see. Test time updates that optimize input statistics, self-supervision, and output measures like entropy have already shown promise. And you can actually extend this idea to CLIP adaptation as well. Right here, the goal is to minimize the Shannon entropy as a self-training loss at test time to make the model more confident of its predictions. However, consider the unimodal adaptation of the vision encoder via entropy minimization. While the image features are adjusted for a specific test batch and domain, the text features pretty much remain fixed, which are still being optimized for the data from CLIP pre-training. Now, let's say we adapt the text encoder only. The generated text features might not align properly with the distribution of the incoming data, which potentially causes misalignment between the modality features. So to demonstrate this idea of entropy minimization, we report results on using entropy as an objective on the benchmark datasets, the CIFAR 10C, CIFAR 100C, and ImageNetC. And we compare the results to a zero-shot CLIP. Clearly, the image and text features are unaware of each other. Hence, we decide adapting both the encoders. As can be seen, the evaluation metric here, which is your classification accuracy, are below zero-shot CLIP on an average in most datasets. Though entropy models a prediction uncertainty, it does not guarantee increasing the likelihood of alignment between the image and text features. So there's a need to make these image and text features aware of so that they're sort of aware of each other. To address the limitations that I mentioned earlier, we propose two loss components that facilitate a more effective bimodal adaptation of CLIP to new domains at test time. The losses that we have proposed focus on maximizing alignment between the visual and text features, while also increasing the separation between the visual features to learn good decision boundaries. So all of this happens at test time with a single forward pass on each test batch. So the first step, as I mentioned earlier, was entropy minimization. In addition to this, as a second step, we propose learning visual and text features that are domain specific and mutually aware by increasing the similarity between the features. So to quantify this similarity between the features, an approach is to project the visual feature onto the text feature because that's how CLIP is pre-trained, right? It's pre-trained contrastively. However, using a direct image feature could be wrong, as pseudo labels or the labels that are generated at test time in a single step might be noisy. So instead, we propose modeling the projection of the class prototype with its corresponding text features. A prototype is useful in this case as it can model the entire class distribution instead of dealing with fine-grained, noisy classes. So at every time step at test time, we project a class prototype onto its corresponding normalized text feature to maximize its alignment. Though the projection matching loss can improve alignment, which we desire, visual features within the same batch could overlap because of a large amount of noise. This leads to CLIP to poorly differentiate between classes. So we propose maximizing the cosine distance between all of the class prototypes in the batch based on the pseudo labels to obtain good generalization and robustness. Overall, the objective is where we minimize entropy and we maximize the projection between modality features and the cosine distance between the class prototypes. And like I mentioned earlier, the layer norm parameters of the text encoder and the vision encoder are updated, and we keep rest of the model frozen. So these are the results on image corruption benchmark datasets, CIFAR-10C, 100C, and ImageNet-C. Each dataset has 15 corruptions at severity level of 5. Each corruption is applied at 5 different severity levels to the test sets, to the respective test sets of CIFAR-10, CIFAR-100, and ImageNet, which are essentially source test sets. And this allows us to systematically evaluate the model's performance under increasing degrees of image degradation. As you can see, our method BATCLIP achieves SOTA results for the online test time adaptation task. It consistently exceeds the performance of of all the prior baselines across all the datasets. Here, we evaluate our method on commonly used domain generalization datasets. So from the table, we observe that BATCLIP does better or comparable across all the datasets and domain shifts to all the baselines. We demonstrate that our method can be generalized and be robust to other domain shifts and not just image corruptions. And all of this happens with a single adaptation step and a fixed global prompt template. You can definitely find more results in our paper. We also show results on datasets with various lighting conditions and camera effects. So our method can be extended to pretty much any sort of domain shifts and also extendable to different VLM architectures. In this figure, we show TSNE plots of visual and text features of a few tasks and compare them against a zero-shot clip with a VITB16 backbone for CIFAR 100C. So with just one single adaptation step, it highlights how our approach enhances alignment with text features, fosters a better class separation and forms more distinct clusters, leading to significant improvements. With that, I'll pretty much wrap it up here. Thank you so much for listening, and I really value your attention and interest. Don't forget to check our paper out to get more insights. Let's continue making AI systems more real-world friendly. Thank you.